this radiation. The thing is, it's coming from the horizon. So it's there's loads of ways to think about it.
How Newton might interpret gravity was adequate to permit us to fly from the Earth to the moon.
With radio telescopes. So that's part of it. But the main bit has been theoretical advances in understanding
at any point. Get yourself lost in the ticking hands of time, contemplating whether our understanding of it is simply the tip of the temporal iceberg. Newton's discovery isn't just a theory. It is a key that could unlock the doors to the mysteries of the universe, revealing a cosmos more complex and inspiring than we ever dared to imagine. How does Brian Cox's new theory challenge our conventional understanding of time? And what are the potential implications for our perception of reality? Join us on a captivating exploration through the annals of time as we delve into Brian Cox's recently unveiled groundbreaking theory.
In all this radiation that's come off the black hole. So it's purely information-less radiation. So what?
On the nature of time in the vast universe around us. Mysteries are waiting to be uncovered, and some of these mysteries involve puzzling aspects of time and gravity, which are fundamental components of our reality. Imagine a world where time behaves unusually. It can either slow down or speed up. Additionally, the force that keeps us on the ground might not be what it appears to be. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes an unexpected turn. Albert Einstein, a renowned name, provided us with a new way of...
So that was a prediction from Einstein's theory, basically. He published it in 1915. And you can predict that that's what one should look like.
Looking at the universe through his theories of relativity. His work laid the foundation for understanding how time behaves under different circumstances, especially when traveling at incredibly high speeds. It all started in the early 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, revolutionized our understanding of reality. In simple terms, it tells us that the laws of physics remain the same for all observers who are not accelerating, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous idea that time can dilate or slow down under certain conditions. One intriguing thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, almost at the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors.
Wow! The 6 billion times the mass of the sun means you multiply that by 6 billion. So these things, the so-called Schwarzschild radius is, I don't know, larger than our solar system, basically.
Perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel along a longer, diagonal path. The time it takes for the light beam to complete its journey should be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the outside observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the stationary observer. In this scenario, time behaves differently depending on your motion. Understanding how things change when they move fast, known as relativistic effects, isn't just a theoretical concept. Scientists use massive machines called particle accelerators, like the Large Hadron Collider, to make particles move almost as fast as light. When things move this fast, we need to think about time in a special way to make accurate predictions and measurements. Albert Einstein formulated the special theory of relativity in 1905, and it changed how we view the universe, especially regarding time and motion. This theory challenges what we might normally think. It says that the basic rules of physics are the same for everyone, even if they're not moving. This is different from our everyday experience, where we might think that if something is already moving and we add more speed, it gets faster. But Einstein's theory says there's a maximum speed that nothing can exceed, and that is the speed of light. In this perspective, events that seem to happen simultaneously for us might not appear that way to people moving around almost as fast as light. Another concept that emerges from this special perspective is length contraction. This means that if something is moving, it looks shorter in the direction it's moving when seen from a stationary point. Then there's the famous equation, E equals mc squared, which shows that energy and mass can transform into each other. This is crucial for understanding how tiny particles behave when they're traveling extremely fast, and also for things like what happens when particles split in nuclear reactions. In the real world, special relativity isn't just a fancy theory. It's something we use in everyday technologies like GPS. When GPS satellites send signals to your device, they're moving, and because of this motion, time behaves a little differently for them. If we didn't account for this time dilation effect in our GPS calculations, your navigation would be inaccurate. So, special relativity teaches us that time isn't the same everywhere. It depends on how things are moving. This idea challenges our usual way of thinking about reality. It's like saying our normal understanding of the universe is a bit off. According to the special theory of relativity, time isn't fixed. It's influenced by motion. Some fundamental concepts, like the speed of light always remaining constant and how energy and mass are connected, have been proven by numerous experiments. But there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory dives deep into the relationship between gravity and how the universe is structured. It shakes up the old idea that gravity is just a force that pulls things from a distance. Instead, it tells us that gravity occurs because space and time are curved or bent. It's like saying, hey, gravity isn't a mysterious force. It's just how things naturally move in the universe. According to Brian Cox's understanding, general relativity means thinking of the universe as a four-dimensional entity, combining 3 dimensions of space and 1 of time. In this framework, massive objects like stars, planets, and even us affect how space and time are shaped around us. We see this shaping as gravity. Imagine space-time like a big, stretchy blanket. When something heavy, like Earth, is placed on it, it creates a dent in the blanket. If you place something smaller, like a ball, near the Earth, it will roll towards this dent. This is similar to how objects behave due to gravity, not some strange force, but a response to the bending of space-time. General relativity provides a powerful explanation for how things move in our solar system, such as planets orbiting the sun. It can accurately tell us how Newton might interpret gravity was adequate to permit us to fly from the Earth to the moon at any point. Get yourself lost in the ticking hands of time, contemplating whether our understanding of it is simply the tip of the temporal iceberg. Newton's discovery isn't just a theory. It is a key that could unlock the doors to the mysteries of the universe,